In this lecture, we will be studying the concept of curvature. So recall, the definition of a parametric curve in R3 is a triplet of functions, which we call parametric equations. X is f of t, y is g of t, z is h of t. And when we put these parametric equations in a vector, we call that vector r of t the position vector for this curve C. And we think of it as this vector, when rooted at the origin, is pointing at time t to a particle that is tracing out the curve in space. To get its velocity vector, we take its derivative, where the derivatives are done component-wise, as long as they exist. We now define the unit tangent vector, and we define it as the direction of the velocity vector, which of course the velocity vector, as we just mentioned, is r prime of t. So if we have a space curve then the velocity vector at time t, so say we're here, the velocity vector is tangent to the curve. The unit tangent vector has the same direction as that velocity vector, but it is of unit length, so it has length 1. And again, you can see that it's natural from the definition. We're just defining it as the velocity vector normalized by its length. Let's look at an example. So we have our classic helix example, and if we want to find the unit tangent vector, first we need the velocity vector, r prime of t, and we differentiate term by term, so we have minus sine of t, cosine of t, and 1. And the magnitude of this vector will be minus sine of t squared plus cosine of t squared plus 1 squared. And we know sine of t squared plus cosine of t squared is 1. And so the magnitude of our velocity vector here was root 2. And this means that our tangent vector is 1 over the magnitude of the velocity vector times the velocity vector. And so this would be 1 over root 2 times the velocity vector, or root 2 over 2 times minus sine of t cosine of t 1. And again, the idea is that this velocity vector at any time t, or the unit tangent vector, is this unit vector that is tangent to the curve. Let's recall from a previous lecture the concept of arc length and arc length parameter. So we defined this arc length parameter in a previous lecture, and the idea was that this s of t, if we have some starting time t naught, and then we have our space curve being traced out, as your parameter increases, then this s of t is the arc length of the curve from time t naught to time t. Now we noted that if we took the derivative of both sides here using the fundamental theorem of calculus, s prime of t, we come over here, we see that t was the upper limit of integration, and to get the derivative with respect to t of this integral, we take t and plug it into the integrand. And so the derivative of this arc length parameter, s of t, is the magnitude of the velocity vector, v of t. If we assume that v of t, the magnitude of v of t, is non-zero for all t, and the idea there is your particle never stops, then that means your function is strictly this arc length parameter, S of t, is strictly increasing, which means it's invertible. And so we can think of t as a function of s. And when we do that, we can think of the derivative dt ds, which will be 1 over ds dt, or 1 over the magnitude of v. This means we can use the chain rule to say that the derivative of the position vector r with respect to s, with respect to arc length, can be written as dr dt times dt ds, again using the chain rule. And we know dr dt, by definition, this is r prime of t, or the velocity vector. And then we just made an argument here that dt ds is 1 over the magnitude of v, which means this becomes v of t times 1 over the magnitude of v of t, which is the definition of the unit tangent vector. So this means that the unit tangent vector is the derivative of the position with respect to arc length. And that will help us with this definition of this idea of curvature. So if t is the unit tangent vector of a smooth curve C, the curvature of C is defined here. We use the Greek letter kappa, and the curvature is the magnitude of the derivative of the unit tangent vector with respect to arc length. So if you think about this, what does this mean intuitively? First of all, the unit tangent vector is, by definition, a unit vector. So its length is 1. It's never changing. But its direction does. Come back here and think about, as you increase the parameter, this unit tangent vector is changing and pointing in a different direction, though never changing in length as you increase the value of the parameter. Here we're saying curvature is the derivative of that, the magnitude of the derivative of the unit tangent vector with respect to arc length. So it's telling you how much the unit tangent vector is turning per unit of arc length. So you can think of it as giving you a way of measuring the bendiness of the space curve. We'll look at an illustration. This is an example we looked at in a previous lecture. And so recall, this is kind of like the track you would imagine a sidewinder rattlesnake would make if it was climbing up a hill in the sand. And the idea here is that in this part of the curve isn't really that bendy. And so the idea is that we should have low curvature. But then when we get to this really bendy part here, the curvature will increase. And you can really think of it as here, when you advance the clock a little bit, this unit tangent vector is not going to turn very much when you move from one point to another. But over here, when you advance the clock a little bit, this vector, this t, is turning very, very sharply around this bend. And so that definition, the magnitude of the vector, derivative of the unit tangent vector with respect to arc length, it's how much that unit tangent vector is having to turn per unit arc length as you move along the curve. We will do this calculation in a little while, but it's worth noting this derivative is not necessarily something easily computable. If you reparameterize your curve in terms of arc length instead of the parameter t, you may be able to use this, but there are nicer results we can use to actually do these computations. And here is one of them. So to actually compute curvature, if r of t is a smooth curve, so r prime of t exists and is continuous, then kappa is 1 over the length of v times the magnitude of the time derivative of the unit tangent vector. And we prove this in the following way. We use the chain rule to say dt ds can be written as derivative of that unit tangent vector dt times dt ds. And dt ds is a scalar, so that can be brought out of the magnitude. So we have dt ds, an absolute value, times the magnitude of that vector, derivative of the unit tangent vector with respect to t. And we argued in the previous slide that dt ds, this was 1 over the magnitude of the velocity vector. And we still have this magnitude of derivative of the unit tangent vector with respect to t, which is the result that we have here. And this is handy because you're typically given your r in terms of t rather than in terms of s. And so this gives us a way to compute curvature, which we can check in this example here. So we're going to use that result, that curvature, kappa, is equal to 1 over the magnitude of v times the magnitude of derivative of the unit tangent vector with respect to t. So we did this example where we had our unit tangent vector was root 2 over 2 times this velocity vector, minus sine of t, cosine of t, and 1. And so in this case, we already have the magnitude of the velocity vector, which is root 2, and we need to get the magnitude of the derivative of this unit tangent vector with respect to time. So the derivative of the unit tangent vector with respect to time will be root 2 over 2. We keep that constant, and we differentiate here. So the derivative of minus sine of t with respect to t is minus cosine of t. The derivative of cosine of t will be minus sine of t, and the derivative of 1 will be 0. And we now need the magnitude of this vector. So the magnitude of this derivative, the magnitude of root 2 over 2 minus cosine of t sine of t 0 will be, well, we can think of it as the square root of, we have minus cosine of t squared plus sine of t squared plus 0 squared. And remember that a scalar can come out of this magnitude calculation. So we have our root 2 over 2 here. And we see that this is root 2 over 2 times the square root of 1, or root 2 over 2. Because cosine of t squared plus sine of t squared is equal to 1. So this curve has constant curvature. And that makes sense when you think about the picture with this helix. That unit tangent vector is always turning in the same way. And so with curvature, you can think of it like driving a car. If you don't have to turn the steering wheel, then you're experiencing constant curvature. So if you were driving, if this was a road, and you were driving up this road, you would have, yes, you would have the steering wheel turned, in the sense that the tires would have to be pointed inward, but you wouldn't be turning the steering wheel as you drove. You would have it turned, in this case you would have it turned to the left, and you would just hold it in the same position. And that's what it means intuitively to have constant curvature. Non-constant curvature means as you continue on the road, you are turning the steering wheel. So We have another formula that we use, and this is typically the most common one that you use to compute curvature. So if r of t is a smooth curve, then the curvature is given by this. So we have the magnitude of the cross product of r prime of t and r double prime of t divided by the magnitude of r prime of t cubed. So these are prime, and here we have r double prime. So this will be what we will use to compute the curvature of the previous example we looked at. So here we need our r prime of t and r double prime. So r prime of t will be 1 minus sine of t, 1, and r double prime of t will be 0 minus cosine of t, 0. And we need the cross product of these. So we need r prime cross r double prime. So let's recall how we do that. We set up our 3 by 3 determinant, I, j, k. For the first row, for the second row, we put the entries from r prime, 1 minus sine of t, 1. And for r double prime, we put 0 minus cosine of t, 0. And we work out this cross product. So we have I times a 2 by 2 minus j times a 2 by 2 plus k times a 2 by 2. So the 2 by 2 for I, erase the row and the column containing I. What remains is our 2 by 2. So we have minus sine of t, 1 minus cosine t, 0. For j, we erase the row and the column containing j, and we're left with 1, 1, 0, 0. And for k, we erase the row and the column containing k, and we're left with 1 minus sine of t, 0 minus cosine of t. And now we go through and do these 2 by 2 determinants. So for the first one, we go top left times bottom right, which is 0, minus top right times bottom left, minus cosine of t. Minus j, top left times bottom right, it's 1 times 0 or 0, minus top right times bottom left, also 0. And then we have plus k, 1 times minus cosine of t is minus cosine of t, minus negative sine of t times 0, so this is 0. And we're left with cosine of t times I. Notice our j component is 0. And then we have minus cosine of t times k. So this is our cross product. So we have cosine of t, 0 minus cosine of t. And recall that our kappa was the magnitude of r prime cross r double prime divided by the magnitude of r prime cubed. So we now need to have the magnitude of this vector here. So the magnitude of that r prime cross r double prime. So we have the square root of cosine of t squared plus 0 squared plus minus cosine of t squared, which will be the square root of 2 cosine squared t, which will be root 2 times the absolute value of cosine of t. The magnitude of r prime, we have the square root of 1 squared plus minus sine of t squared plus 1 squared, or the square root of 2 plus sine squared t. And putting these two together with our result tell us that the curvature for this curve is root 2 times the absolute value of cosine of t over the square root of 2 plus sine squared t. And this, again, as you run the clock, this is going to be the measure of the bendiness of this curve. It's going to be the measure of how much you have to be actively turning your steering wheel as you move along this path, along this road. And again, this formula gives us a very convenient way to do this calculation.